Okay, so I think in the last lecture we have spent a lot of time to describe, um, how we can use the insights that we obtain from the free energy curve analysis, right? And these curves are, you can consider, are informed from the regular solution model that we have. And we show that, from these curves, you can use double tangent construction to understand, the range of composition, a molar fraction of one of the, atoms, and within which the system will stay as a solid solution, and what are the corresponding molar fraction or composition that gives you a two-phase coexistence state that is more thermodynamically favored. And also we show that you can very conveniently collect all such information and represent such information on the so-called phase diagram. Okay, so and I think in the last lecture we very kind of in detail went through that how we construct this very simple type of phase diagram, which is a prototypical example of silicon germanium phase diagram, and more importantly, we construct this phase diagram by using the free energy curve analysis, right? So we examine the free energy curves at different temperature, and for each temperature, we do the double tangent construction. We identify the compositions during which the two-phase coexistence is more stable, and we kind of convey or equivalently represent such information in the phase diagram by drawing the timeline and identifying these two compositions, right? And we do that for different temperature. This will allow us to construct a liquidus and solidus that separate different phase regions, from the liquid, solid, and coexistence regions, right? This is how we construct the phase diagram from the free energy analysis. And more importantly, we showed that, if you're given a phase diagram, and you can recover a lot of information that you get from the free energy analysis, and even some additional information, right? Like we show that if you focus on a particular composition, you can follow the evolution of a microstructure by inferring, at what different stages in different phase regions, what the microstructure looks like, right? And you also can identify theoretically, when the solidification starts and when the solidification completes, right? By looking at the intersection of the composition line with respectively the liquidus and solidus, right? This is when you do a vertical line in the phase diagram. And then we show that if you do a horizontal line, which we call tie line in the phase diagram, you can also get a bunch of information. And the first set of such information includes the equilibrium composition of liquid phase and solid phase that you get from the free energy construction, right? And we show that these compositions are independent of your initial choice of your, your system's composition. You can have, any composition within this range, but, at this temperature, like 1,200 degrees Celsius, when the system separated into two different phases and coexist in this case, the equilibrium composition of each phase can always be these two numbers, independent of what is your initial composition, right? And we also say that, okay, then what initial composition going to play a role? What is the role this initial composition we call omega naught play in the system? Okay, it does not going to determine the equilibrium composition of the two phases, which are determined by the tie line, which is associated only with temperature, right? But the composition of the initial composition of the system does play a role to determine how much solid phase you have, or the amount of solid phase you have, and the amount of liquid phase you have in the system. And we briefly indicate that this is given by the so-called level rule. Okay, so in order to use this, you need three composition. You need your initial composition, and you need the composition of the equilibrium liquid phase and solid phase, right? And these two compositions, the liquid and solid phase composition, are obtained by constructing the tie line for a given temperature. And this omega naught is given, right? You prepare your system with this initial composition. So knowing these three numbers, and we can use the level rule to estimate the amount of liquid phase and solid phase. Now, in particular, the liquid phase in the system is proportional to the so-called liquid arm, which is computed as the solid composition minus your initial composition. And the amount of solid phase is proportional to the so-called solid arm, which is obtained by, you're taking the difference between your initial composition and the liquid composition. Okay, so this is called level rule because your solid arm is determined by the liquid composition and the liquid arm is determined by the solid composition. Okay, so I think in the last lecture, this is what we stopped in the last lecture, if I remember correctly. So I think I give you an optional homework that, to derive this level rule. I don't know whether I have a chance to think about it, but today I thought that I should, go through this together with you. I don't know why I have an extra line here, but anyway, so this is the diagram, right? We show that, okay, you can use the level rule to estimate the fraction of the phase or the amount of the phase if the total system weight is given, right? Why we have a level rule here? So the basic consideration for this is very straightforward. We can use two conservation laws, namely the conservation of mass and the conservation of solutes. Okay, so by the conservation of mass, I simply mean that, if you look at the system before and after phase transformation, now suppose before the transformation, I'm in a single liquid state, right? So the total mass of the system is given by this capitalized M. And after the transformation, I have two different phases, right? I have liquid and solid, right? So after the transformation, my system have two phases, and this is the mass for the solid phase, and this is the mass for the liquid phase, right? But before and after the transformation, no mass is lost. So the mass is conserved, right? Before and after the transformation. Now there's another thing that is conserved in the system. Okay, can you tell me what that is? The total mass is conserved. And what else is conserved in the system before and after the transformation? The solutes, right? The solutes are also conserved.
Yeah.
Right? Yeah, right. Because initially you put this amount of silicon in the system. After the transformation, we only have a redistribution of silicon, right? Initially, it's all in liquid, but after the transformation, some more silicon are gonna get into the solid, and less silicon gonna exist in the liquid. But you just have a redistribution of the solutes. The total amount of the silicon in the system is still conserved. So this is the second equation we have. So the first one is the conservation of total mass. The second one is the conservation of the solutes. So why?
I have a small question here. So we are considering the silicon germanium system, right?
Not necessary. This is a prototypical. You can imagine this is silicon germanium, but in general, for any AB system, you should have this.
Oh, okay.
Yeah.
Thank you.
No problem. So this is very generic. It doesn't really matter what exact system you have. So so the first one is conservation of mass, and this one, the second one, I call the conservation of solutes, because if you see what is the left-hand side of this equation. So what is omega naught? Omega naught is the initial composition of the system, right? If you prepare the system at high temperature as a homogeneous liquid state, omega naught is going to give you the overall composition of this liquid, right? And what is this? What is ms plus ml?
Is the total mass of solid and liquid phases.
This is the total mass of the system, or you can say this is the total mass of the initial liquid state. So if you take omega naught times the mass of the initial system, what this quantity gives you, this is the total amount of B atom in the system, right? Or silicon in the system, if you want to be more concrete. Make sense in the case? So this is basically the total amount of silicon or B atom before transformation. And what is this term? Omega S times ms. Ms is the mass of the solid phase. Omega S is the composition. So what do we have here? This is the total amount of solutes, B atoms in the solid phase, right?
Yeah.
And for the same reason, this is the total amount of solutes in the liquid phase. So out of these two together, you get the total amount of solutes. You get total amount of B atoms after the phase transformation. And because we say, and as a matter of fact, the solutes are conserved before and after the transformation, so we have this equation also holds. Does this make sense to everyone? Okay, so now once we have this equation, it's very straightforward that we can combine the terms that have this mass for the liquid all together and group the terms with the mass of solid on the right hand, and you already see that the level rule is emerging, right? So this is the mass of the liquid phase, but it's a ratio, so we can say this is also a mass fraction of the liquid phase. This is a mass fraction of the solid phase, right? And that fraction is proportional. The ratio between the two fractions are proportional to the ratio of the two arms. So if you recognize what this is, this is I think there's an issue with the sign, but it's fine because they cancel one another. This is basically the liquid arm, which is this guy, right? The solid and omega. So the difference between these two are the liquid arm, and this is a solid arm, omega and L. Okay, so that's just, the very simple way how to derive level rule, which is very straightforward, just using the two conservation equations. Okay, so yes.
Professor, so the first equation is the law of conservation of the total mass of the system.
Yes.
In the equation, is it the mass of the solute that is conserved?
Yes, the mass of the solutes, or the amount of the solutes, because the solutes has a fixed density, right? You can, you divide the density, you get a number. But anyway, so this is a mass, yes, more rigorously speaking.
Yeah, thank you.
Yes, no problem. Yeah, so that's the level rule, okay? So, yes, this is a liquid arm and that is a solid arm. So you have a level rule. This is very straightforward. And they're very simple application of level rule, right? So if I give you, the system at this temperature, as I think you've probably seen this many times from an undergrad level introductory material science class, but I want to quickly mention this as well. So if I give you this phase diagram and ask you to compute what is the fraction of the liquid and solid phase associated with this temperature, 1,200 degrees Celsius and 30 weight percent of silicon, how would you do that? It's very straightforward, right? So basically what we do is that you first find this tie line I already give you. This is 1,200 degrees Celsius. You get the equilibrium composition of the two phases. So this is going to be your omega L, this is going to be your omega S, right? And then you find the composition line, which is 30%, okay? And then you can compute the liquid arm, like as this one, right? And you can compute a solid arm like this one. And then you get a fraction of the phases. If I give you a total mass of the system, say I have 100 grams of the alloy, and you can easily compute the mass for each phase. Okay, that makes sense to everyone? I think this is very clear. Okay, so that's all I want to say about this simple phase diagram. Again, the point here is to show that, okay, we can represent information we get from the free energy curve analysis as different temperature and kind of very conveniently and concisely represent all that information using the phase diagram, right? And because the key information are the equilibrium compositions. And more importantly, given the phase diagram, you can go back and recover a lot of information that you get if you were doing this free energy curve analysis. You can go back and forth and get a lot of information, both qualitative about the phase in the system and quantitative about the composition and even the amount of each phase in the system. Okay, so that's basically what we have described using this example. Okay, so now I'm going to speed up a little bit because I hope this is already clear to everyone. So let's look at a more complex scenario. So this is, again, I would say this is probably the most simple phase diagram you can ever have for alloy because they only have a single liquid region and a single solid region and a solid liquid coexistence. But we mentioned that, in general, for alloy, you would have at least, two different solid phases because usually the two elements that are mixed together, they have different crystal structure, right? One of the example for that is the lattice system. So now let's look at what happens in those cases. Okay, so here I already give you the typical lattice phase diagram, okay? And the reason why that you have two different solid phases is because, the A-rich structure and B-rich structures have different solid crystal structure, right? In the case of lattice, A is a FCC, alpha phase is a lead-rich FCC, and beta phase is tin-rich BCT or BCC. But they have two different solid phases. So we're gonna see how. So in this case, once you want to do the free energy analysis, you have to simultaneously keep track of three different curves, right? Correspond to three, single phase state. Respectively, you have a liquid state, which is right here, and you have an alpha phase, which is one of the solid phase, and you have a beta phase, right? So in order to analyze the system with this different type of phases, we need to keep track of the free energy for all three phases, in this particular case. But the analysis would be very similar. So again, we're going to start with a high temperature state. Okay, this is T1, which is also labeled here. Again, what we did here is that we just draw a line across the phase diagram. This is illustrate the particular temperature, and we label each different segment of the line with the corresponding phases. Okay, and you see that if you choose this T to be very high, like in here, we just have a homogeneous liquid, right? So this means that the liquid curve is going to be lower than all of the other two free energy curves. So your system is stable as a single liquid phase across entire composition line. But we won't show that because that's trivial, and we already showed this for the more simple system. So now we start with a non-trivial temperature T1, okay? And you have this scenario. So clearly here you have, three different curves. This is my beta phase, and this is my alpha phase, and this is my liquid phase. Now, if you look at this free energy curve, look at this free energy plot, does beta phase play any role in determining the stability of the phases?
No.
No, because it's up high, right? The free energy is too high, so it won't play any role for any composition. And then we just have these two curves, alpha and L, right? The alpha phase and the liquid phase. So in this scenario, it's pretty much going back to the liquid and solid phase analysis we did before, because only I'm worried about two phases. So in general, there will be a region of composition where you have coexistence, right? And then for very low composition, your solid phase can dissolve this small amount of B in A. So the solid phase at this temperature can remain to be a solution, a single phase. And at a high temperature, at a very high composition, the system is stable as a liquid, okay? Because B has a lower melting point, right? So if you dissolve A and B, you can dissolve them in a liquid state. Okay, so that's basically give you the three-phase region, and we represent this three-phase region along this temperature line. So what do we have is that I start from B equals to 0 and to this value, okay, probably I don't know exactly what that is, maybe 5% of B. Okay, for that very tiny region, you see that this is a solution or solid state solution of alpha phase, right? Like in here. So you have this region to be the alpha phase, and in this very narrow region, probably from, I would say 5% to maybe 15%, like here, okay, you have coexistence. And then for larger composition, if you keep on increasing, the liquid phase is going to be stable, right? So now this is the black line corresponds to this free energy analysis, and even for this temperature, you have three different phase regions: single phase alpha, alpha plus liquid coexistence, and the liquid. Okay, so that's the same thing. Now, if we do the same thing and do a lower temperature analysis, okay, which corresponds to this red line here, okay, you see that now. Okay, the alpha curve and beta curve all move relatively lower, and the liquid curve move relatively upper. Okay, so in this case, you clearly see beta phase begins to play a role in here. Okay, but still, if you look at the low concentration regime, okay, you have very similar scenario as we did for the first one. You still need only worry about liquid, alpha, and coexistence. But on the right part of this diagram, okay, you see that beta curve is much lower. The reason why is that in this case, we have a B-rich system, so a solid phase that consistent with the B-rich microstructure will play a role here, which is the beta phase, right? And then what you need to do is you need to consider the possible coexistence of a solid beta phase with the liquid. And indeed, you can construct such a region, which are here. Okay, so again, without going through the details, which are the same as we did before, we have on this red line, we have to pin down more than one coexistence region, right? Because we have a liquid alpha coexistence, but also we have a liquid beta coexistence. So basically, these two regions are represented here. But the way that how we do this is similar. Just mark down these these composition, and then eventually we're going to connect them to construct the liquidus. This is liquid alpha liquidus. This is liquid alpha liquidus. This is liquid beta liquidus, but they're all liquidus, separating from pure liquid phase and liquid plus solid coexistence. Okay, so that's the red line. Again, it's a little bit more complicated. You have to worry about the coexistence region of two different solid phase with liquid, but again, it's still a binary construction for each coexistence, right? Now, here is the more interesting scenario. So if you keep on lowering the temperature, you're eventually going to achieve a very delicate temperature such that these all three curves, they're just aligned in a way you can construct a not double tangent for two phases, but you can construct a triple tangent, right? Which is common to all three phases. Does this make sense, or does this understandable to everyone? I just want to make sure.
Yes, yes.
Okay, so what does this mean? Is very straightforward, right? You can still consider the two you can first consider alpha liquid coexistence and consider alpha beta liquid beta liquid coexistence, and then you need to add the alpha beta coexistence, right? So basically, what this means is that at this very unique temperature, okay, how many coexisting you have, or how many phases can coexist at this very unique scenario?
3.
3, right? You see, because all the 3 phases, the share, the atoms in all these 3 phases share the same, exactly the same chemical potential. So here you have 3 phases that are in thermal equilibrium. So they coexist. Does this make sense, everyone? From what we have here, right? And it turns out that this 3-phase coexistence corresponds to a very unique point, okay, on the phase diagram, which is right here. So, this unique is not because from this analysis, we know that it's the 3-phase coexist, but also when you represent all this information on the phase diagram, now what you see that you just have alpha, single phase alpha region, and you have alpha liquid coexistence, and you have liquid beta coexistence, and you have a beta phase, right? You see, we're missing one region. We don't have a liquid, right? So we're missing an interesting region. So in this case, from this analysis, we say that at this particular point, I should have a 3-phase coexistence. But where is that coexistence region on the phase diagram? Is this a clear question?
Yeah, it's a point. It's not.
It's a point, right? You see that? It's a point. So, we mentioned that in the alloy, when you have a coexistence, you usually have a region, right? You have a region of temperature, you have a region of composition. But in the binary phase diagram, when we talk about 3-phase coexist, okay, you only have a single point that can achieve this.
What's on the right side of this line?
This part?
Yeah.
This is liquid plus beta.
But it's also 3-phase region, right?
No, this is only 2-phase.
I mean, just below is also alpha plus beta.
Below this is alpha plus beta, but we're talking about a particular temperature, right? We're looking at this particular temperature and we're changing the composition.
But this line shares both the region, right?
This line does not show any region of 3-phase coexistence. So what is the meaning here? Tell me, what is the meaning of this point?
I thought alpha transforms to alpha plus beta.
No, at this particular point, you have liquid plus alpha. At this particular point, you have liquid plus beta. We'll show this later, okay? Now, what happens if you further cool the system lower from this point down?
Liquid turns to beta.
The liquid simultaneously transforms through this point. The liquid is going to simulate the remaining liquid from here, you have alpha plus liquid, right? But if you further cool from this point, the remaining liquid, going to further transform through exactly this point to both alpha and beta. Okay, we'll show that later. Yes.
So this 3-phase coexistence, the 3-phase existing simultaneously,
Yes.
will only happen at a particular temperature and a particular composition, right?
Exactly. Yes, exactly. That why is a point, right? In this point, you have a particular temperature and you have a particular composition. Only at this particular point, you have 3-phase coexistence.
Okay.
Does that make sense to you, to everyone? We'll show this. It's a little tricky, but we'll show this.
And I have one more question, Professor.
Sure.
The green plot of the free energy versus composition, is the liquid free energy curve touching that triple tangent there?
Yes, it's supposed to be touching, but this is the best I think we can get. It's supposed to be touching, but it's shift a little bit, but it's supposed to be touching. Yes.
Thank you, Professor.
Thank you. Yes, so that's that, right? So this is a little tricky, but we'll show this in an example, and you'll see how they can all work together. Okay, so let's keep on going, so we can finish this phase diagram construction at least. So yeah, so if you keep on lowering the temperature, and in this case, that your liquid phase is going to out of the picture, right? Because at very low temperature, the free energy curve going to be very high. And only have both alpha and beta phase that play a role in here. And now you're going back to the 2-phase region. You're worrying about 2 free energy curves. So you're going to have single alpha phase region, single beta phase region, and alpha plus beta coexistence region, right? And then you have 2 types of solidus that give you this. So and if you can further lower in the temperature, and you see that the boundary going to move this part, this alpha solid is going to further move left, and this beta solid is going to further move right, due to the reduced solubility limit as you lower the temperature. Okay, does it make sense to everyone for this? So again, when you connect all the dots together, you're gonna get the phase diagram like this. Okay. Oops. Why I still have this? I'm sorry. Let me clear all. Okay, good. So that's the Latin phase diagram. Does it make sense to everyone? This is how we have this. And now this phase diagram is interesting for a number of reasons. Let me see how I want to talk about this. So first, I think this diagram is typically refers to as a eutectic phase diagram. Okay, do we know about this? I guess we should know, right? This is typically we call eutectic. But do you know what is the meaning of eutectic and why it's called eutectic?
Yes.
Okay, so eutectic in Greek words means lower, right? It means or easily melt. So, but why we call this easily melt? What's the difference between you see from this diagram and the one of the germanium silicon?
Because the melting point of the mixture of the phases, mixture, the melting point of the alloy is lower than both the components, both the constituents.
Exactly. So in the case of silicon germanium, if you think about it, melting point, if there's no well-defined melting point, but if you see the coexistence region, it's kind of a linear interpolation between the two, right? Let's go back and see this. I think it's interesting. These are, see that? So, this is a high melting temperature metal, and this is a low melting temperature metal, right? So when you mix them together, you'll see that, based on the composition, the approximate coexistence region is gonna be roughly speaking, an interpolation between the two, right? So this means that if you add more of the high melting point alloy, high melting point metal, you're increasing the melting point of the whole alloy, right? And if you add more of the low melting point metal, you're decreasing the so-called, or in quotation marks, the melting point of the alloy. So this makes sense. It's interpolate between the two, right? But in this case, in the eutectic, so first there's a well-defined melting point in the system. And we said that for most alloy, right, melting will not occur at a single temperature. Is this clear? Melting is not going to occur at a single temperature. It's usually occur over a region, right? Or freezing. Like in here, if you look at A, you start with a liquid, but you have to go through a finite range of temperature for coexistence, and then you're getting into the liquid, solid case, right? So for alloy, typically melting or freezing going to occur through a range of temperature, but there's a very unique point on this phase diagram where the melting or freezing occurs like if you're in a pure state. What is that point?
Eutectic point, which is 81.9%.
Eutectic point, right? You see why? Because if you look at that, this point is playing the same role as this point and this point. Does it make sense to everyone? So you start from a liquid state and you cool the system. The transition does not occur over a range of temperature. It's occur exactly at this temperature. And after you cool below this temperature, the system becomes solid. This is like, you mix them together as an alloy, but this alloy has a well-defined melting temperature. Okay, so that's one interesting about this. And second, how this melting temperature of the alloy compare with the pure A and pure B, or pure silicon, pure lead and pure tin.
So pure lead is having 327 point something, and pure tin is having 231. So it's much lower than both the components.
Exactly. So when you mix these two together, right, you get apparently a system that behaves like a pure metal, has a well-defined melting point. And on top of that, this melting point is 183 degrees Celsius, which is listed here, which is lower than both of the melting point of the individual metal, right? So that's why we call this eutectic, because when you make it as an alloy, it's more easily melt. Okay, that's why we call it eutectic. But anyway, there's more information than that, right? So we're not just explaining the name, but you see this is a very interesting point for this type of system. And it appears that this eutectic behavior is quite commonly seen in many different types of alloy. Okay, so that's why I spend time on this. Anyway, that's one thing. Okay, but again, let's go back to this phase diagram. And let's do the same practice as we did before, right? If you remember what we did for the silicon germanium, the first thing we do is that we choose different composition vertical lines, and we go through these lines from a high temperature state to low temperature state, and I want to see what information we can extract from these analysis. Okay, so we have now give you 3 composition A, B, and C because you're going to see different type of evolution history, and we're going to go through them together. Okay, so are we good? Okay, no more questions on this one, right? So I'm going to move forward. Okay, so let's do A first. Okay, so I start with a liquid. Okay, which if you take a small observation window and look at the system, you're going to see a homogeneous liquid state. There's no microstructure. Okay, so I have a liquid. Now, what happens if I lower the temperature and get into the two-phase coexistence region right here? What are you going to see in terms of the so-called microstructure of the system?
So liquid state with some alpha phase.
You're going to see that, there's a majority of liquid, if you look at this in the top, right, at high temperature, and there will be some small alpha phase forming in the system like this, right? It's very similar to the germanium silicon, okay? So now what if I further cool the system into this alpha region?
So it will be alpha phase only without any liquid.
It will be going to be alpha phase liquid, but importantly, because we know this process is a nucleation and growth processes, so you're going to see a texture or polycrystalline microstructure associated with the solid alpha phase, right? That makes sense, everyone? So now, what is the composition of this alpha phase?
It's lead dominant. Lead dominant. It's lead rich.
What is the number?
The number is
10.
10 with percent tin, right? This is a composition line, and we have a right number on this. So we have 10% tin in the system, and we know that it's a homogeneous phase. So every single region of alpha phase will have this 10% of tin, right? Mixed with 90% of lead. Did that make sense to everyone? Okay.
yes.
So now before I show the last picture, so we know that if I further cool the system, what you're going to have, what phase you're going to have if I further cool the system down here?
So a alpha plus beta.
You're going to have alpha plus beta. Does this make sense to everyone? Because
Yes.
I'm now in the two-phase coexistence region, right? Right? Now, if I just choose this like 100 degrees Celsius, give me a rough estimate. What are going to be the corresponding equilibrium composition of alpha phase and beta phase?
Approximately those. So there will be alpha phase. So there will
Be
full
around
composition.
99. Beta will be around 99 and alpha will be less than 10.
Alpha gonna be, let me do this for you so we can have a. So I choose 100 degree, right? This is not very low temperature, like this. So I would say my alpha phase, so we know that now we're going to have alpha plus beta coexistence. This is from the phase diagram, right? And I know that alpha composition going to be roughly 5%, I would say probably 6 or 5. And the beta going to be 90, 98, probably 98, 99%, right? So what this tells you, get the numbers. And what is a beta phase that is 99% tin? It's almost pure tin, right?
Yes.
So what do you think? What do you think that what happens? After you cool the system from this single alpha phase to this alpha plus beta phase region, what do you think happened? What is the mechanism that gives you this
Diffusion from beta phase, like alpha is going from beta to lead is going from beta phase to alpha phase?
Yeah, so basically we have two phases. We know that the system going to separate into alpha plus beta, right? And you see that the beta phase is very, very pure, almost a pure tin. So this means, what does this mean atomic wise? If you think about a microstructure, so these tin atoms get clustered together, right? They get clustered together, form almost a pure tin phase.
So will we get any precipitation or what?
Exactly. So if you think about it, that this example or that this process is very similar to if you have initially a sugared water at high temperature, but now you lower the temperature and you decrease the solubility of sugar in the water, what would you see? What's going to happen to the sugar initially dissolved in the water?
Separation.
They take out, they precipitate out from the solution, right? and they form a aggregate that's almost a pure sugar with some small amount of water molecules trapped within. That makes sense to everyone? Okay, so what happens here, if you start from this alpha phase to the alpha plus beta coexistence, what happens physically, or at least the mechanism wise, is very similar to what happens if you have a initially, a sugar water with sugar well dissolved in the water at high temperature and cool the system so the sugar precipitate out. That's the same, virtually the same mechanism or physics. So because the solubility of tin in this lead-rich alpha phase gets smaller and smaller, right? So you can hold, so the solution, the solid solution in alpha phase cannot hold that amount, relatively large amount of tin atom in the system. So these tin atoms are gonna get clustered together through diffusion, and they're gonna come out as a separate phase, as precipitate in the system. That makes sense to everyone? Okay, so now in order to understand, so there's one more thing, okay? If I give you this alpha structure, the difference is that from the water sugar example, you're gonna have a solid precipitation from liquid, and these solid will eventually, get, they're gonna settle down the bottom of the container. But in here, we're talking about precipitation in a solid solution. So where do you think that precipitation gonna occur, and why?
Along the green boundaries.
Along the green boundaries, right? Or on the triple point. So from they're gonna have a high probability of occurrence at these defects, right? Does this make sense to everyone?
Yeah.
Okay, so we're gonna explain why this is the case later, because this is they're occurring through a nucleation processes, and we'll show later that in a solid solution, when you talk about nucleation, you have to worry about the diffusion. You also have to worry about the elastic energy or the mismatch of the lattices. And it turns out that whenever you want to insert a solid with a different volume than other solid, it's better for you to do this on the green boundary where you have a lot of packing defaults. This is going to release the stress energy or strain energy introduced by this particular processes. Okay, but that's the microstructure. So you see, this is, again, it's quite interesting that from we analyze this phase diagram, and it doesn't show you the microstructure looks like, but from the process that we go through, we can get information on what microstructure looks like, and this precipitation microstructure turned out to be very important for engineered material, right? For the lead tin, probably it's not that important, but for example, a steel, which is a alloy made of iron and carbon, we know that to control the size of this, we call it's not pure carbon, but you have precipitates which are very hard. It's carbon fluoride. Is that the right word? But it's a compound which is very hard, right? So these are particles that disperse in a soft matrix. So you control the amount of these particles, their morphology, and how they distributed will play an important role in determining the mechanical behavior of the system, as you can imagine, right? So that's why through all the trouble, understand what will be the microstructure looks like from the phase diagram, and use that information to engineer the microstructure to achieve, desirable properties. So that's for A.
So, I have a question. So the example that you have just given, the iron carbide formation. So is it related to martensitic transformation? Or?
No, it's different. We'll talk about that later. Martensite is a non-equilibrium transformation. It's diffusionless. It's a very fast, transformation. We have a lecture describe those, but it will be the very late stage of the class. That's kind of a exception from what we typically talk about. Okay. Anyway, so let's move on.
Professor, I have a question here.
Sure.
In the last diagram there, we know that beta is around 99%, greater than 90%, and we know alpha is less than 10%. But isn't that misrepresented in this diagram here of the microstructure?
No, in the microstructure, I didn't show you any composition. I only show you the faces.
But shouldn't the beta, the white patches, be dominating the microstructure then?
No, the beta is tin, right? If you start with 10% tin and you start with only a small percent of tin, even all these tin cluster together, do you think these tin gonna take a majority part of the system? The majority is still gonna be alpha, which are lead, right?
Okay.
Does that make sense?
Yeah.
Okay, if you didn't see this clearly, let's do the construction of timeline. Okay, so I can't remember, it's 100 degrees Celsius. Okay, so tell me, what is the beta arm?
The one on the right.
And this is the alpha arm. Whoops. And that is the alpha arm, right? This is the alpha arm.
Okay.
And this is the beta arm. So which one is dominant?
Yeah, alpha. This is based on the lever rule, right?
It's based on lever rule and based on a lot of interesting things. You don't have to see exactly from lever rule, but think about this. You're dissolving only a very small amount of tin, and all this tin came out, right? In this solution, still lead is gonna dominant, and lead is alpha phase. You don't have to use lever rule to see this. There, a lot of things are consistent that you can rationale this, right?
Yeah.
Lever rule will be the last thing to use.
But if we continue decreasing the temperature, will these precipitates grow?
It may grow a little bit, but not a lot.
Okay.
Yeah, they will just remain like this most cases. So for a number of reasons, in equilibrium they may want to grow a little bit, but if you cool the system lower than 100 degrees Celsius, virtually diffusion going to get very, very slow, right?
Okay, yeah.
Cool. So let's move on. Yes, this is So let's move on to C, right? So we talk about A, and we think we're clear, and let's move to C. So this is the interesting point about eutectic transformation. So I'll show you what exactly I mean by coexistence three-phase. So this is interesting because the microstructure is you only have two scenarios, right? You only have a liquid, and you only have this. I already showed you the microstructure. So anyway, yeah, you only have this alpha plus beta, but you can see, this is what alpha plus beta looks like for path A, right? And you can see the microstructure here is quite different from the alpha plus beta you get from that path. This is path C, right? We call this a eutectic microstructure. Okay, so yes, this transformation. So in here, this eutectic system has this unique point, which we call eutectic transformation. The reason why is because it's a well-defined transformation at a single temperature, like in a pure metal, right? So we call this eutectic transformation. And we'll spend a little bit more time later to investigate the diffusion and how this occur, nucleation, etc. But for here, I just want to quickly mention that the eutectic transformation, because it occurs very quickly, right? This is distinctly different from the nucleation and transformation that you have for growing a alpha phase like this, right? And here you have a lot of time, a range of temperature allows you to do the diffusion and grow, into this globular alpha phase, right? Typically we call this globular or primary alpha, and then eventually have this. But in the eutectic, you see the transformation can occur at a single temperature. So if you want to separate, because initially you have, this is your composition, right? So let me show you. So in order to have eutectic transformation, what is the composition you're going to have for the overall liquid? You have to have exactly this composition, which is 61.98% of silicon, right? And then if I cool the system a little bit, so after I transform into alpha and beta phase like this, what are the corresponding composition of these two phases?
18.3 for alpha and 97.8 for beta.
So these compositions are quite different from the liquid, right?
Yes.
And we know that, okay, how can you achieve these different composition? Only through diffusion. Does that make sense to everyone? But then we have a dilemma, right? We have to make sure the system have huge separation of composition, but yet it's gonna occur very quickly. So what do you think is the most efficient way of doing such separation? Instead of having, growing a very large region of alpha and beta separately, what I do is that I have this alternating, fluctuations of density, right? The alpha region has smaller amount of beta. So what I can do is that So what I can do is that I can simply repel the actual amount of tin into the nearby regions, which can eventually form beta. And for the same reason, the beta can repel the actual amount of lead into surrounding nearby regions, which eventually going to form alpha. So that's why, again, it's a very brief rationale. That's why you're going to see this eutectic microstructure, which composed of stripes of very thin stripes of alternating alpha and beta phases. And the thickness of the stripe is basically diffusion controlled. We'll analyze this in later. It's controlled by diffusion temperature. Okay, but this is, you can imagine, right? This is a very efficient way of separating the tin and lead, into different regions. You just do this in the nearby region. You don't do long-range diffusion. You just repel what you don't want to nearby regions. So it forms this alternating stripes. Okay.
Below that is the microstructure, the microscopy image of that kind of structure, right?
Yes, this is an image, but I don't know what this image is. Probably it's optical image. Yes, I'm sorry, I didn't show you a bar, but the size of this image is roughly 100 or several hundred microns, probably 100 micron across. Okay, so this is a real image of the eutectic structure, and you didn't see this ordered way of separating, and you didn't see the same spacing across all the sample. It's because you probably have some grain structures underlying the growth of the eutectic, and in here because you probably have a different temperature, so they have fluctuations. So you didn't see the perfect stripe structures, but this is the way how we typically illustrate that. Okay, and this
it's not an electron microscopy image, right?
I don't know. I think optical image is good enough to show this. You just polish the sample and you do some etching, and then different phases going to have different etching depths, and then this will see show the signal using optics. I don't think it's SEM because the features are too large.
Yeah. Okay. Thank you.
That's eutectic, right? So this is all I want to say about this, because we're going to reserve more details later. So again, eutectic, I think the key point here is that eutectic is a very fast transformation. It's well-defined thermodynamic phase transformation from a single liquid phase simultaneously to two different solid phase alpha and beta, right? And at this transformation point, right at this particular point, right at 183 degrees Celsius, you see that liquid coexists with alpha and beta, right? So during the growth of the eutectic, you see this part is liquid, and then you have this portion of solid growing, and in the solid you have both alpha and beta phase. So that is how you achieve coexistence of three phases. Does this make sense, everyone? Yes.
Yeah, this is for tin and lead system. It's possible that it's not always these lamellar structure.
No,
right?
This laminar structure is universal in the sense that is intrinsic to the mechanism of the nucleation and the growth of this eutectic transformation. It's intrinsic to the transformation, not to the system. So if you have other like aluminum copper system, but you undergo eutectic transformation, you're going to see a very similar structure to this one, like this one, because this is probably not lead tin. I don't know what this is. I just randomly grabbed this on the web from website.
But this is not for all the combinations.
Of course, no. This is only for eutectic. Is well defined.
No,
it's only going to occur for this. Yes.
Eutectics, also for eutectics, it has to form these lamellar structure.
If you have a system prepared at eutectic composition for the liquid, so when the liquid undergo the eutectic transformation, it will always result in this eutectic microstructure. It doesn't really matter what is your system. It doesn't really matter whether it's lead tin or A and B or copper and aluminum. As long as it has a eutectic and you prepare the system at eutectic, after the transformation, you will see a structure like this.
Okay.
Good. So yes, this is about eutectic. Let's move on. Okay, we have, I think, running out of time. And so now, we understand what happens in A and what understand what happens in C, right? Now here is the tricky point. Okay, what do you think is going to happen in B? So yeah, that's just what we're going to do. Okay, so yeah, let me where start. Yeah, let's start from the beginning. There's another way that I can present this, but let's do this in normal way. So if we start from B, so we choose this lead tin phase diagram and 30% of tin, right? This is your composition. Okay, and then what happens at this high temperature state is very straightforward. It's still a liquid with no apparent structure. It's homogeneous, right? And also it's kind of boring if we just enter into this alpha plus liquid region where you have this, right? We know this very well. So my question for you is that now if I further cool the system, okay, where's my mouse? Further cool the system and allow the system to get into this alpha plus beta region, what the microstructure going to look like? Is the microstructure going to be like eutectic, or the microstructure going to be just like the, precipitation? that we show for A, or it's kind of a mixing between the two?
It's just the mixing of the two phases, not
Mixing of two.
precipitation.
No, it's precipitation.
So in here, we know that you're going to have a precipitation, right? You're going to have, you know, this alpha phase and you have a beta come out. Let me just draw this for you. So like if along A, right, we know that you're going to have, you know, these things. These are small beta grains, and then you have these alpha grain boundaries like this, right? This is going to be a precipitation type microstructure, okay? And in here, we know you're going to have eutectic microstructure, which is difficult for me to draw. So this is the best I can do. You have this. Now, what do you think we're going to have here?
It's just the mixture of two phases. No, without press, or it will be like a single grain, maybe consisting of no.
So in order to understand the microstructure, we have to understand what happens during the solidification, right? So you think about this, you know, I'm not asking to make a guess. I'm asking you to follow the evolution history of the system and the rationale, what the microstructure looks like. So first, we know the microstructure definitely going to have alpha grains. Does that make sense?
Yeah.
Because they already formed, right? They're not going to dissolve back into the liquid. So definitely we're going to have alpha. Right? And then you see, so the microstructure, whatever we're going to see here, going to be based on this one. And then there will be some further development, right? Does that make sense, everyone?
Or maybe it will form a core shell structure or some beta deposited on the around alpha.
Why? Just give me a reason. Following the evolution history, why this your rationale? What is your rationale? Don't do just a random guess.
Yeah. So first, when alpha is forming here, so from the liquid, the most of the alpha phase, which is lead rich, is actually solidified. So the liquid becomes tin rich, and then it starts forming beta phase, and that's why beta phase will just deposit or fuse with the alpha phase.
You mentioned a very important thing, is that because when you're forming these alpha phase, right, the alpha phase is lead rich, so it's repelling the tin into the liquid. That's very important. This part is correct. And then you have to follow that. And there's a quantitative result due to the growth of the tin composition, as we show here. Okay, that's a very right direction. So if I ask you, okay, what is the initial composition of the liquid phase? If we start here, what is the initial composition?
So it's 30% tin and 70% lead.
It's 38% of tin, right? What is the composition of liquid phase if you look at here?
It will be more than the lead will be more than 70%. I don't know exactly how much, but it will.
Let's look at tin.
No, sorry, tin. Tin will be more than 30%. Yeah.
Tin will be roughly 40%, right?
Yeah, 40%. Yeah.
Now, if we further lower the temperature, what will be the composition?
48, 49. So
48, 49. If we further do this, it's going to be 52, 54. Now, remember that, you know, what we're doing this is that we're keep on lowering the temperature, right? So the system gonna, you know, keep on growing in terms of the alpha phase, but there was still some liquid remaining in the system. More importantly, what happened to the composition of the liquid as you cool the system?
Became tin rich.
The composition of the liquid become tin rich is increasing in terms of the weight percent of tin, right?
yeah.
Does this make sense to you? Now,
Yes.
Now let me do this. Okay, so now let's keep on lowering the temperature until we reach here. At this temperature, which is 133.1 degree. Let's just a little bit higher, but you know, from diagram it's the same. What is the composition of the solid? Of the alpha phase? 18.3.
18%.
Now the following question is very, very important. What is the composition of the liquid phase?
0. No, yeah, 0.
What is the composition of the liquid phase?
Yeah,
61.9.
Yeah.
How you get a composition of the liquid phase? You do a tie line construction, you get the intersection of the tie line with the liquidus. This is the intersection of the tie line with the liquidus. What is the significance of the 61.9%?
It's tin rich extremely, like it has more tin.
what is the significance in terms of a possible phase transformation?
It's a
Eutectic
Eutectic point.
So if I take this system here, right? So suppose this is my current system, and I have these alpha, globular alpha, primary alpha that already formed. So I don't need to worry about them. When they're gonna change, right? Now, if I so suppose that this is a picture of the system right at this point, I have some liquid, I have some alpha. Now, if I further cool the system, what's gonna happen to the alpha phase?
Alpha
Goes to
alpha
will
stays
be
like that, but the liquid will convert into, like, it shows lamellar structure, the eutectic structure.
Exactly. Alpha gonna stay as alpha because this won't change anything, right? But the liquid now gonna go through pathway C, right? Because you see you're pushing the liquid composition right to this eutectic composition as you lower temperature to grow more alpha. So right at this particular temperature, your liquid is already have a composition that is right the eutectic composition. So it's gonna go through a eutectic transformation and form something like this, right? So what happens then? You're combining these two. Oops, this is supposed to be a plus sign. You combine these two, and you get.
We have the pure grains, like the pure grains with alpha with no stripping, and we have for beta phase we have some stripped grains.
So basically, this lower temperature, you have more alpha, right? But you still have remaining liquid, and then all of these liquid are going to transform into eutectic, right? Eutectic structure. So now is before the transformation, you have this alpha embedded in a homogeneous liquid, but after the transformation, what you have is roughly the same amount of alpha, but embedded in the eutectic microstructure like this. Does this make sense to everyone?
Yes.
Right before the transformation, you have this alpha embedded in the liquid, right? After that, all the liquid is going to transform into eutectic, but of course, you're going to have alpha going to affect the growth of eutectic. You're going to have different orientations of these stripes, but it's still going to be a eutectic. So this is what you get along B. Does this make sense to everyone?
Yes.
Again, you see, this is, do not make any guess. This is rigorous information that we can obtain from the phase diagram analysis. Okay, so this is very important. And another important thing is that we get this particular information of microstructure because the phase diagram tells us quantitatively how the composition is going to change, how the liquid composition change as you lower the temperature to drive the solidification, right? So this diagram contains a lot of information, more than meets the eye. Okay, so this is eutectic. Now, this is
so sir, I have a question, like simple question. So I don't know exactly what is the composition of the soldering wire that we use for
the composition of what?
The soldering wire. The one with it's a wire that we use for soldering electronics and some circuit boards and
the solder, yes. Yeah, I don't know. I think it's probably
it's 40,
30 something.
Yeah,
35. I think it's 35 or 35, 40. Yeah, I think it's perhaps 35 tin, I guess. I can't remember exactly. Yeah, but let's talk about it later. Let me finish this because we're kind of rushing the content.
Okay.
Professor, I have a question here.
Is this related to the content or?
Yes.
Okay, sure.
What is the time scale of that eutectic transformation? How?
There's no time scale, because in here we're not talking about time. We're talking about temperature. Because we're lowering the temperature to induce the
equilibrium transformation, right?
Yes, equilibrium transformation. So you take whatever time you want to make the system in equilibrium.
Okay.
Yeah, no problem. So that's it. So yes. So the point here I'm making is that not only you can draw these very pretty pictures qualitatively, and you can actually compute and predict the amount of each of the phase, each of the structure you produce in the system. Okay, so I don't think I have time to go through this in detail, but yeah, let me show this. So this is again a real picture of this structure, and you can see that these large guys, these are globular alpha, or sometimes we call this primary alpha because they form during the initial nucleation and growth processes, and then you see that the existence of this alpha clearly affect the eutectic structure. They change the orientations of these things, especially near the surface of these globular alpha. But nonetheless, schematically, it's going to be a mixture of eutectic structure embedded. You have these primary alpha phase embedded in the eutectic structure. Okay, so that's the real image. I'll just give you an idea. Okay, so this is quite different from the schematic, but it's a good illustration. Now, here is my question. Okay, so not only we can draw this very beautiful plots like these, we can also quantitatively predict what are the amounts, what are the mass of each phase. Now, let's distinguish 3 different phases. So in here, if you look at this microstructure, how many phases do you see?
3.
How many phases do you see?
Oh, phases are 2.
2, right? So you have alpha, which are these whatever color you see. It seems to me like a purplish thing, pinkish stuff. But you have this pink alpha phase and you have the blue beta phase. You have 2 phases, right? But you have 3 type of microstructure. You have this alpha phase in the globular microstructure, the alpha phase in the eutectic microstructure, and alpha phase in the beta phase in the eutectic microstructure. Right. So, and the reason why we're interested in this is because the amount of each type of phase in combination with microstructure determine the mechanical property. Because the globular alpha is because the shape, or they're large grains, typically they're softer, right? But these stripes are much harder. So the amount of each phase is going to determine the mechanical properties. So typically we want to distinguish how much globular alpha you have, how much eutectic alpha you have, and how much eutectic beta you have. Does that make sense to everyone? So we can distinguish different type of phases of different shapes, from the transformation. Okay, so now this is a question for you to think about. I think you should have seen how to do this from again, more elementary level of class. So given the time constraint, I may not have time to go through, but I still want to throw this question to you as an optional homework problem. Okay, so let's basically see if we have a 100 gram, okay, a small amount of this lead tin alloy potentially used as solder, okay, with 40% of tin. So this corresponds to exactly this line, right? This is 40%. Find out the weight of eutectic alpha. Okay, I just want to the mass, or just to read the matter, the mass or the amount of eutectic alpha out of this 100 gram of alloy. How many gram of these stripe-like alpha you have?
18.3.
No, that's the composition. That's the composition. I'm asking the mass. Okay, so think about it. It's not a straightforward question. You have to do some calculation, pretty sophisticated calculation. Okay, but I can outline an idea for you. So first you have to do this in 2 steps. Okay, following this pathway. You start with this, and at this point, can you compute what is the amount of the globular alpha or primary alpha and the remaining liquid right before the transformation?
Yeah, using the global.
Can you compute that?
Yes, I think 61.9 minus 30 divided by 61.9 minus 18.3. It's like M alpha we figure out.
It's almost right, but the composition here is 40% instead of 30. So you have 61.9 minus 40, okay?
Yeah.
Yeah, so that's gonna give you, is this the liquid arm or the solid arm?
Solid arm.
Solid arm. This is gonna give you the relative amount of alpha, right? And then what you do, you can do the similar thing. You use 40% minus 18 point, I think it's 18.3, right here. So you get this liquid arm, right? And when you get these 2 arms, you get the relative fraction of the 2 faces, and because you have 100 gram of overall alloy, so you can compute the actual mass of the liquid phase and the actual mass of the alpha phase, right? Does this make sense to everyone? Using this particular point and lever rule, does this make sense? This is very important.
Yes.
Okay. Yes. And then you move on, right? Because you're not interested in the primary alpha. I'm only interested in the eutectic alpha, right? Where does the eutectic alpha come from?
From the liquid.
From the liquid, right? From the liquid. So let me, because this two looks pretty much the same. Say for the liquid, I have 55 gram liquid and 45 alpha. So now I only need to worry about that 55 gram liquid, right? And then I can use lever rule to determine if my liquid undergoes a transformation to produce alpha and beta phase. Now after this transformation, what is the amount of alpha, right? I can use another lever rule applied to this only 55 gram of liquid. Does this make sense to everyone?
Yes.
because now the liquid have a different composition. This is my new composition, right? You start with this composition, but now your liquid have this composition. So I have to use a new level rule based on this new composition. This is my liquid. What is the composition of this guy? 61.9%, right? What are the additional two composition I actually use? I actually choose this. This is going to be my omega naught, right? What is omega alpha?
18.3.
What is omega beta?
97.2.
So this is my new alpha arm, right? Does that make sense to everyone? The omega beta minus omega naught. This is my new alpha arm. So this arm over the total length of this, which I say probably 40%, right? And times the 55 gram of liquid, which is a fraction of the overall 100 gram. And that's going to give you the mass of eutectic alpha. And for some reason, you can compute the mass of eutectic beta. And if you add all of these together, you should get 100 gram. Okay, so that's a very quick way. But again, you know, I think this is not quite sophisticated, but you have to realize you need to use the phase diagram in two different ways. The first one is to compute using level rule composed of this three composition before the transformation, right? To compute the amount of alpha and the liquid phase. And then you have to use a different set of composition. You have to use these three, right? To compute what happens to the liquid in order to compute the amount of eutectic alpha or eutectic beta. Okay, so yeah, that's basically, I wouldn't give you the calculation, but I think it's pretty straightforward. You know, roughly estimates, you know, we have 55 gram times 40%, right? That about, you know, 28 gram of eutectic alpha, which, you know, I think is reasonable. Okay, and you can do the calculation in more detail as an optional homework, but I'll keep on going for now. Okay, so I think that's the last one I want to mention for the eutectic phase diagram. These calculations and informations that you can get, right? You have a quite different, you know, much richer microstructure that you can play with, you can engineer. There's one more thing that I want to quickly mention, which I didn't show here. So we analyzed three different pathways, A, B, and C, right? But what happens if we choose a composition right here? You know, what the microstructure kind of looks like.
Beta will be more, and there will be eutectic too, eutectic formation too.
I claim that you're going to have a microstructure very similar to this, but with the color of purple or pink and blue exchanged.
Yes.
Does that make sense to everyone?
Yes.
Yeah. Okay.
Instead of primary alpha.
Exactly, because you see that the pathway is very similar, but instead of growing alpha first, you're growing beta, right? And you're decreasing the composition of the eutectic and the of the liquid, and you're going to have eutectic. So you're going to have beta grains embedded in the eutectic microstructure. So basically, change the color, reverse the color of the two phase, and you get that microstructure. Okay, so this is very straightforward. So I think that's clear. Okay, now move on. Okay, so this is, you know, I think that we talk about two, you know, very ideal but very prototypical phase diagram, right? One is the germanium silicon, the other one is lead tin, which has a eutectic. So in real engineer alloy, I'm going to quickly show you this, but because this class is not about physical metallurgy, we won't spend too much time on this. But I just want to show you, in reality, you know, the phase diagram may look quite complicated and something like this. For example, this is aluminum copper phase diagram. Okay, so, and you can see the complexity of the phase diagram. So I wouldn't explain each of these, but you have different phases defined in these and different regions, and some of them are not probably well defined or hypothetical phase regions like that. Okay, but the thing that I want to you know, emphasize is that what we describe here is important. We're not describe phase diagram like this, but you see there are a lot of information that are similar to what we analyze, right? It doesn't really matter how complicated this phase diagram is, you know, at least for aluminum alloy, right? For aluminum copper, you know, because copper, in this case, we typically, what we do is that we add a little bit of copper into the aluminum. So the copper is going to serve as the solid solution strengthening mechanism. We make aluminum, this alloy stronger, yet we do not lose a lot of advantage concerning the lightweight of this metal, right? Aluminum is very light, but it's very soft. So we strengthen aluminum with a little bit of copper added. And with that logic, the key thing that typically when we analyze the system, we're only interested in this regime. So do I have, yes, exactly. So we're only interested in a very low copper composition. And you see in this regime, we basically only have this, precipitation mechanism, or at most we can have some of the eutectic mechanism. So that's why, what we describe about these phase diagram, the simple phase diagram will be very useful, okay? And another system that I want to quickly show you is this guy. This is a very small portion of the full steel phase diagram. This is iron carbon phase diagram. Okay, as you can see, again, even we look at a very small composition, like this is 0.76%, very, very tiny amount of carbon added, even less than 1% added, but you have a very rich phase behavior. Again, we're not going to go through this in detail because this is not a physical metallurgy class. But I just want to point out there are many different solid phases can form for iron, and for the system, you can alpha phase. You have alpha phase. You have the gamma phase, which is the typically called austenite, and you have this delta phase, which is high temperature phase. Not quite interested. Typically, you need to worry about the gamma phase and the iron carbide, which is a very brittle, hard ceramic phase. Okay, that mainly composed of carbon and embedded some iron atoms. And the existence of the carbon iron carbide is crucial to the mechanical properties of the system. If you add too much of these, the steel going to be very, very hard but brittle. If you add too less of them, it's going to become more like a pure iron, which is soft. So we want to engineer the composition of your carbon and to basically produce the right amount of these iron carbide inclusions or precipitates, right, to have the right mechanical properties. One thing that I want to point out is that in here, if you look at this region, do I have, yes, look at this region, okay. So this looks very similar to the eutectic transformation, right? Because you have a single phase that, and when you cool the system, you simultaneously transform from the gamma phase to two different phases, alpha and iron carbide. But can anyone tell me, is there any difference between this particular transformation and the eutectic we just talked about?
There's no liquid phase.
Exactly. Here, the transformation is from a single solid phase, from the gamma phase, which is a solid phase, right, into two different solid phases. Okay, so it still have a eutec behavior, right, but it's not from the liquid. So we call this transformation the eutectoid transformation. Okay, to highlight that now you have a single solid phase and then transform into two different solid phases. Okay, and there's some terminology about this transformation for the steel. So if your composition is higher than 0.776%, people typically call this hyper-eutectoid. And if your composition is lower, this is called hypo-eutectoid. And if you have even higher composition, this is called cast iron. Okay, again, this is some terminology. And if you happen to see these, they're referring to the different composition of carbon you put in the system. Okay, so again, if the point here is to tell that we can use a lot of information we get from analyzing the two very simple phase diagrams and apply them here. For example, if I ask you to compute, I give you a composition and ask you to compute what is the amount of each phase after the transformation, it should be very easy to do, right? Because the procedure will be very similar. So one example is here.
I have a question, small question here. So suppose if we take any composition of any metals or any alloys, so is there always a eutectic point, or it's not necessary that we always have, we must have any eutectic point?
I don't know the answer for that question, but for most of the engineer alloy people already make, you do have either eutectic or eutectoid. Okay, so let's move on. So again, this is to show that how the information we get from the eutectic analysis can carry out here. So it's very similar. Again, you start with a gamma phase, right? And then if you follow a composition line that is right here, you basically now first get into this alpha plus gamma coexistence. And in this particular case, alpha going to precipitate out, right, as these individual particles. Okay, so here. But then if you further cool the system down, okay, you're going to get all of the remaining gamma phase going to undergo a eutectoid transformation to form this type of structure. Okay, so when you enter into or get into this particular point, this is a microstructure, and these large black things are the primary alpha grains, and the white things now are the iron carbide. Okay, so that's but you can see the microstructure looks very similar to what we discussed from the eutectic transformation, and all of the analysis that we introduced there can be applied here. Okay, but in here there's another terminology that I want to quickly talk about. People typically call these stripe-like eutectoid microstructure composed of both iron carbide and some of the austenite. They call this the pearlite. Okay, it's the eutectic mixture of alpha phase and the iron carbide. Okay, so that's pretty much all I want to say about this phase diagram. And also you can do some calculation, as I said before, in a very similar fashion that we described for the eutectic transformation. So the key will just be identify the correct composition to use and apply the correct level rule. Okay, so I will skip that for sake of time. Okay, so this is summary of the topics. I know for the last two lectures, I think we have a lot of information, but mainly on to deriving a phase diagram based on the free energy curves, and we do a Maxwell construction or double tangent construction. We get information about equilibrium composition, and we express or represent that information at different temperature into the phase diagram, and then we construct a phase diagram, and then from the phase diagram we can get a lot of additional information that equivalent for analyzing the free energies, but in a much convenient way, right? We describe different type of phase diagrams and show that some very simple principles that we get from this prototypical phase diagram can apply to more complex system. Okay, so with that, I will stop. Okay, so it says stop recording.